Institute of Space Physics in Uppsala. It has a few departments, and the main one is in Kiruna, but there's also a place in Lund and Umeå, the smaller groups. And my talk has many names, and that is because I will show Cassini data, and there are some rules on how which persons has to be on talks in that case. I will first of all talk about the role of the ionosphere for the atmospheric evolution of planets, and it's related to the paper we did in astrobiology, me and Janna in Kiruna. But my focus of this talk will be about Titan, and my focus will be on plasma escape and how the processes we see around Titan, how they can be important for understanding atmospheric evolution of planets. And the other one is that we have some very new results regarding the chemistry in the deep ionosphere of Titan. And we see an enormous production of molecular ions, organic molecular ions, in the deep ionosphere. It's dominating, these heavy ions dominate the ionosphere below 1,000 kilometers. Okay, so I understand this is interdisciplinary. I understand there's biologists here also. So space physics is not astronomy, but related. We usually make in situ instruments, and we put them on spacecrafts, and we measure in space, and we most often study the relationship between solar activity and various space environments around planets, in particular the Earth. And on Earth, the magnetic field is very important, while around more or less unmagnetized bodies like Mars, the solar wind, which is expanding from the sun, hits all the planets, and if it's unmagnetized, the solar wind hits the atmosphere directly and erodes the atmosphere, while the processes in magnetized planets are some of the atmospheric erosion is somewhat more complicated. I will show you some data further on here. So first of all, a brief overview of understanding, and the understanding is, when it comes to the details, rather low. The one we know most of is the usual Yee's escape, which is a distribution, the tail distribution of particle population in the atmosphere. When it reaches the escape velocity, it can be removed from the planetized body. And it's a thermal process, and it actually is only important for the very light atoms, hydrogen and helium, for atmospheric evolution. While for other species in an atmosphere, heavier species, we certainly have much larger effects by various non-thermal mechanisms, which I will talk about today. There is hydrodynamic blow-off, where you have an extreme UV condition of the sun or star, and that is, and by so you disappear, you push away the atmosphere. You have photochemical heating in some cases, that with a release of energy from excited states, and but this is a purely chemical region, and we think it's only affecting light neutrons. Ion pickup and subsequent sputtering of the upper atmosphere is much more known process nowadays. I will show you how it is, but you have ions created in the upper atmosphere, and then when the solar wind comes, it will be affected by the electric field in the solar wind, will be picked up by the electric field, so it will start to go gyrate around the interplanetary magnetic field and therefore escape from the planet. So this is a non-thermal process, but it also favors light ions. And by that I mean H+, H2+. And then we have a thing called non-thermal ion ionization by parallel electric fields or various wave processes, plasma wave processes. And it has to do with local deposition of the solar energy to the planetary atmosphere, or ionosphere in this case. And then you have an electrodynamic coupling that accelerates the ions outward. That is the major and dominant process for oxygen escape from Earth, for instance. So that is affecting heavy ions very much. And then there is a large-scale momentum transfer, where the solar wind dynamic pressure, ram pressure, and electromagnetic forces push the bulk plasma around in the ionosphere outward from the planetary body.
What is the escape speed for Titan?
Escape speed for Titan is not much, it's something like 1.6 meters per second. Okay, but the Titan, as you will see, is a very extended atmosphere. It's a very fluffy object, and a very extended ionosphere as well. And you can see you have I will show you.
1.6 kilometers per second.
Sorry.
1.6 kilometers per second.
Yes.
Yes.
So here you have some measurements of the non-thermal escape mechanism around the Earth and Mars. Now also we have such measurements around Venus. And here you have some escape rates for estimated while you're sampling data when you orbit these bodies. So it's around 0.5 kilo per second around Mars. It's mostly O+ and O2+. And Venus it's a little bit larger, O+ ions. And for Earth it's 1 kilo per second. And this looks rather small maybe, but if you add up for a year, it's between 50,000 to 60,000 tons a year that disappears from the atmosphere. So if you calculate this over 4 billion years, you start to understand that okay, Mars' atmosphere will disappear in about 100-200 million years, for instance, while it will take a longer time for planets like Earth and Venus, which have a much more substantial atmosphere. So for a long-term atmospheric evolution, these processes need to be known, need to be considered by models. Here you see from the cluster spacecraft, it's actually 4 of them around Earth, and this is H+ and O+ measurements of outflows in the tail from the Earth. And in this case it's Mars Express and the Aspera instruments, which shows O+ escape and also O2+ escape from the planet Mars. So these escape rates, they start to become more and more certain, and also the processes, the mechanism behind. Dependence on solar activity. There is such an activity. The solar activity varies by about a factor of 3 in the well, okay, radio emission is this f10.7, but in the UV it can be a difference in some cases up to over a factor of 10 from time to time. And if you have such differences, change variability in the solar activity, and you can plot here this activity level with the influence or the escape of various ions in the case of Earth. You can see it's a dramatic increase for high activities. So for O plus O flow, you can, for this rather small change of a factor of 3, you can gain a factor of 100 variability in the O plus O flow. And considering that the early Earth most probably had a much higher, or rather the early Sun was much more active, and the UV flux around 4 billion years ago is estimated by some people to something like 15 times that today. We think it's very important to have this in mind. While the H plus outflow is not, it's so variable, and that means that you will have a large contribution to the oxygen over a hydrogen ratio of this atmosphere, which is affected by the sun. So, did we have a large outflow of oxygen on early Earth, is the question. This is from cluster measurements. On Venus there has been a measurement of a factor of 20 in the ionotail density, and that means also the flow. And in Mars, with the new Mars Express measurements, there seems to be similar things going on. I go on. It's also dependence on geomagnetic activity, which is related to the solar activity. And you can see a rather strong coupling between the AP index as a measure of the activity of the Earth's magnetosphere and how much activity you have in the auroral zone, which couples to the major part of the magnetosphere. And you can see a clear relationship for increasing geomagnetic activity and solar wind dynamic pressure, and that means the solar wind pressure instead of the extreme UV activity, and also the interplanetary magnetic field, IMF. And you can see that these kind of activities are related to our auroral zone, and from the auroral zone most of the O plus outflow from Earth is detected. Okay, so in our zone there are processes that makes the ionosphere escape. And it depends on various mechanisms that has been identified over the years with several spacecrafts. Here is what we call broadband electrostatic waves, or lower hybrid electromagnetic ion cyclotron waves, and also Alfvén waves. And I will not go into details on these mechanisms here. Just say that they have been identified as the sources in the ionosphere for spinning up the oxygen ions, and by the magnetic moment you push them out to space, out in the tail, and then lose the ions further on. Okay. So, we have a solar wind interaction with various atmospheres. And the solar wind is the particles of hydrogen and helium coming from the sun all the time with a speed of 300 to 1,000 kilometers per second. And it's not many, it's a few particles per cubic centimeter. But it has a large dynamic pressure. And in a magnetized body, the plasma, planets with dipole magnetic fields or magnetic fields, this plasma is charged, so they will become magnetized and will not penetrate this magnetic barrier of a planet. They can enter some ions through the cusp, and you often see that with the spacecraft. If you have an unmagnetized body like Mars, Titan, Venus, then the solar wind will reach the atmosphere directly, and you can have a direct interaction with the atmosphere or rather the upper parts of the atmosphere, the exosphere, we call it. The question is, what was the early Earth like? And today Earth have a very strong magnetic field, and you have a boundary further away. On the other hand, you have strong and nonlinear processes that makes ion outflows coming from the Earth zones anyway. Or was it maybe a weaker magnetic field, which is indicated by some considerations in geology? And in that case, the solar wind, which was probably much stronger, more stronger in the early days, 4 billion years ago, than hit the atmosphere directly. But even in these cases, there often is some remnants magnetic fields, and due to induction of currents in the conductive ionosphere. So the ionosphere kind of reacts to the flowing plasma here and sets up currents that makes magnetic field, which protects the ionosphere in this case. So in both cases, there is a strong magnetic field between the ionosphere and the shocked solar wind flow, which comes and wants to interact with the atmosphere. Okay, let's skip the last case there. So, okay, I show you a bit of UV here. And this is the sun in extreme UV by the SOHO telescope. And you can see activity here. And this is from November 2003. And you should focus on this activity here. This is just to relate to what kind of mechanism on the sun that makes these shocked solar winds. We call them coronal mass ejections, and how variable they are. I mean, it's a 25 days rotation here of the sun, you see. And these are then active regions, solar spot regions, and one of the largest explosions on the sun happened at this time. And if you focus on here, you will see something. And you see some dots here, and that is very energetic particles coming from the various places and hitting the thing. Now, look here. There. And just to see what's happening. And that storm caused aurora down in the Iraq, and Malmö didn't have electricity for half a day. It induces quite a lot of electric fields on these long lines of current. There is an even larger explosion soon here, but it's pointing away from the Earth, fortunately. But it had quite some dramatic effects on Earth, and you could see the iron outflows increased immediately from the spacecraft around Earth. It's there, so you can see these. You can see nice coronal mass ejection starting here, expanding forward. Okay.
And the energy of the particles is on the order of 10 to the 10 dB, right? That we saw also that hit the detector.
It varies. There is a UV burst in electromagnetic radiation, X-rays, and then you have a shocked solar wind of more thermal particles. You can say it's around 10 dB, coming with speeds of in this particular case was up to 2,000 kilometers per second, and hits the magnetosphere. Then you have also, before that, reaching Earth, you have these very energetic particles, which can be the energies you say. And these, some of these can even reach the cloud layer, I guess. Okay. I need to fasten up here. So this ionopause, the location of the ionopause, where you have the ionosphere bounded by, is dependent on the extreme UV flux activity of the sun. And you can see, so it varies with the solar cycle. So the ionopause will go out when you have low solar activity, and then will shrink when you have higher solar activity. So for Venus in particular, you can see a difference between the two cases of some of their over almost 2,000 kilometers, which is rather large. And if you have an extended exosphere atmosphere, like in this case here, then you have a higher ionization rate by the UV radiation, because you have more neutrons around, and ionization of otherwise escaping neutrons in this case. And then they will be trapped more easily by the magnetized ionospores, which is here, in induced kinds. In the case of an unmagnetized body, there is still magnetic fields around it. So that would actually decrease the Jeans escape of hydrogen and helium. So you will, and at the same time you have an increase of heavier ions from these planets, and a decrease of the traditional thermal escape rates. And also higher ionopause means less neutrons around. So for the case of Mars, it's very important because you have ion pickup. There are ions that are created from neutrons out here, and when they are picked up by the solar wind electric field, they start to gyrate away from Mars. So that is also reduced and affects mostly light mass ions. Here I just showed it. So you have ions high up, and they kind of picked up and flow away from the planet by the electric field of the solar wind. This is the case of Titan. Okay. Then there is the solar wind dependence also of the particles coming from the sun. It's an interesting effect here, because if you have a strong and stable interplanetary magnetic field, you will basically have no change. But if the direction of this magnetic field will start to change, you will have to start reconnection, and will actually shrink the magnetic barrier, because you lower the pressure balance between the solar wind dynamic pressure and the magnetic pressure of the unmagnetized body. Or the thermal will also add up. It depends a little bit on the thermal pressure of the ionosphere. And if you have a strong solar wind, as in maybe in early Earth, then you have a lower pressure balance altitude. So you really push away this, and you have a higher escape rate. Okay, I think I skipped that one. So I sum up this first part of the talk of the early Earth ionosphere. At that time, 4 billion years ago, or before, was most likely a high extreme UV for ultraviolet intensity. Most likely also a much higher solar wind dynamic pressure. And here we're talking about a factor of 15, maybe even larger. And there is a similar thing for the solar wind here.
They were not actually more like a factor of 100 larger. The sun was
4.5 billion years ago, yeah.
Yeah, I see. Okay, fine.
Okay, yeah, it's true. But around 4, when the life starts to it's more like 15. It decreased rather
quickly, isn't it? Yeah.
Okay, and that is from studies of nearby G stars. And to get the solar wind dynamic pressure, you study in Lyman alpha, I think, nearby stars, and use various stop or shift techniques, I'm not sure, but I know they have a few stars which they have determined the solar wind of nearby G stars. Okay, so you probably have a strong and active interplanetary magnetic field. Sun is the source. That means you have a larger oxygen escape from these planetary bodies in the neighborhood, and a larger heavy species outflow. So if this is so much more efficient, then one could think of an early atmosphere, at least the upper parts of it, that is rather reduced chemically rather than oxidized, as suggested by casting method, for instance. Okay, and yeah, the point is that there are so many processes here that are important that it's not easily taken care of in theory, that one should take all these early atmosphere models a little bit with a grain of salt, please. So it doesn't need to be a fully carbon dioxide atmosphere.
Just to clarify this, I mean the escape helps oxidizing the atmosphere. So of course before that it must
no, the oxygen is primarily removed from the atmosphere, so it gets more reduced.
But the H, yeah, but
the H is not by the mechanism I have been talking about.
I see. Yeah.
No, okay. It's many unclear parameters in this, but we are trying to gather the space physics knowledge and try them to start at least speculate about what the early Earth atmosphere and the evolution of atmosphere plants is. And it has importance because it's a lot of particles that disappear with these kind of mechanisms. I think I go on instead. Let me go to Titan instead. I'm in charge of I manage one of the instruments on board, the Cassini spacecraft, the Lagny probe, which is part of the radium plasma wave science instrumentations on board Cassini. So this is my main work these days, is to get this data okay. And one of the subjects is plasma escape from Titan, and I will show you some data here. And first a little bit of Cassini regions. Cassini is the spacecraft, orbiting spacecraft around Saturn now, and each orbit it passes very close to Titan. We are up now at 50 Titan passes now, and we have some 15 to go, I think, for the extended mission. So, and Huygens is the lander, which was released 2005 and landed on Titan in the beginning of the year there. And there's a long way. I started with this 1990 when I was a PhD student, trying to get some people to listen to me, to have an instrument on board. It worked actually. And then you build the instruments and so on, and that takes a few years together with the engineers, and then you send it away, and 7 years more, and in 2004 it was there. 14 years after, I suggest you should have instruments on board. Now it circulates there, and the mission will continue until 2010, and then they will park probably the spacecraft in safe orbit. They have not decided yet. Okay, the spacecraft is big, so this one is little, but that's the instrument I'm responsible for. It's a Lagny probe. It's basically a weather station for plasma charged gas, giving density, temperature, speed on this gas. And this happened to be in Swedish, sorry. Okay. So it's actually this one. This is the sensor, and we put it on the potential, and then we sample either positive ions or negative electrons, and then measure the current. It's a very, 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 very good ampere meter, basically. And I will not go into details, I think I skipped that. And what do we do with this one around Titan? Well, Titan first. The reason why why Casino was funded is because Titan is such an interesting object. It is large, like Mars, have a very dense atmosphere of nitrogen and methane, mostly nitrogen. It is not so much oxygen in it, it's parts per billion, something like that. So when the infrared spectrometer on Voyager 1, which just passed this moon far back, then they saw quite a lot of interesting organic species in the atmosphere. Here we have hydrogen cyanide, cyanogen, HC3N, and there was quite a lot of various nitriles and hydrocarbons detected. And that was strange because it was such a cold place. Why is there so much organics around? The chemical rates should be very low, since the temperature is minus 183 degrees Celsius on the surface. And then you have also this enormous photochemical smoke around Titan here, which was so dense that you couldn't see the surface at the time. And that is made up of very large organic chains which are clumped together, and it's an aerosol, organic aerosol. So what is that coming from? And we think it has to do with the interaction of space from the Sun and from the energetic particles in the magnetosphere of Saturn. And here we have Titan moving around Saturn, and we have lots of energetic particles as well as the EMV from the Sun, ionizing the upper part of the atmosphere. So I will show you one flyby here, how it could look like. We have all 40 flybys now. You have what we call a co-rotating plasma, and that is a magnetospheric flow, kind of solar wind-like, that hits the upper parts of the atmosphere. And then you have the sunlight, in this case comes from here and a little bit below here. This is to Saturn, and this is north then of Titan. This is just one flyby geometry, so we have one each. And these things here is just where we start to detect cold or cold dense ionospheric plasma. Okay. So here is the first results we had from the first Titan flyby, published in Science. And this is the density, and you can see the density is rising here. So this is the ionosphere density up here. And later on we could identify that this first peak is mostly from the extreme UV radiation ionizing, and the second part here is more likely to be electron impact ionization from the magnetosphere of Saturn. And there's a lot of dynamics going on, and it's quite extended here. It's more like a Titan radii away. So this is lots of cold plasma 7,000 kilometers away from Titan. And then you can see the magnetic pressures of the co-rotating magnetosphere and the thermal pressures here. And you have a region here where they start to match each other. So below, closer to Titan, the thermal pressure dominates, while outside the magnetic or dynamic pressure we also have of similar value is dominating. So here is what we should call the ionopause here. And we still have quite a lot of cold plasma outside here. Okay, so the escape flux from these first measurements was something like a few 10 to 25 ions per second. About 1-2 kilos per second. So that's quite much also. And if you integrate that over the age of the solar system, you realize that quite a substantial fraction of the nitrogen atmosphere must have been escaped. It turns out also that the exosphere around Titan is also losing quite a lot of neutrons from Titan, and it's even larger escape rate for this particular case. So it's so Titan's atmosphere must have been very much denser in the past. I talked several times, so maybe even up to 20-50 times denser. Okay, I will not go into details here, but here's the potential we sweep the probe with, and this is just the current we sample. This is electrons from the ionosphere, and this is the ion part we see. And what we see is the ionosphere proper here, and then we have something which an extended region which kind of disappears with a kind of trails off with a scale height of around 320 kilometers. An exponential decrease from here. And this is part we call the exo-ionosphere, and it's actually being slowly removed from Titan. And we are now investigating what is the causes for this removal of this very dense cold plasma. And this is a paper by Audrey, a student of mine. And this is a study we go on with, and we compare it with theoretical simulations. It's a one with Roman Modulo. It's a hybrid code where for a particular flyby, T9 in this case. And it's interesting because this is the sunlit side, and this is the RAM side. So you have quite a lot of solar ionization here, and you have quite a lot of magnetospheric ionization by electrons on the other side. And it causes kind of a two tails with cold plasma. And the first one has quite a lot of heavy ions, CH4 plus type. It's actually H2Cn plus also here. While the other tail here is more hydrogen abundant. And that is because you have, we think, a charge exchange of the hydrogen and oxygen with the upper atmosphere here. It's a ram flow of oxygen and hydrogen ions directly. And it's charge exchange higher up, where it's more lighter ions, and therefore you have a higher density of lighter ions. So you see two kind of mechanisms at the same time in action here. You have solar UV radiation and a bulk outflow of heavy ions, and then you have a charge exchange reaction region with the flowing plasma giving more H+. And you can see, compare the data we have. This is the density, the blue and the red here, and then you have the model. So here's the first heavy ion peak, and then you have the second one over here. And it's a rather, well, maybe not perfect, but rather good agreement. So.
It came from above, yeah, on this right-hand plot.
Yeah, it came here.
Yeah.
Crossed the heavy iron tail, which we see there, and then it came down here, and then you crossed the other tail here.
Does one also see a signature of the cusps? Because you mentioned earlier you would expect some effect of
and
inflation at the cusp region.
This is not a cusp, because Titan is unmagnetized.
Yeah, right.
But we do have what we call a magnetic pileup region, where the flow, magnetic flow, induces currents in the ionosphere, which creates a magnetic field that pushes away the incident flowing ions. So that protects. That's kind of an induced magnetosphere, we call it.
But these ion densities are not measured by the. You must have a mass spectrometer also to get this data.
No.
Even the Langmuir probe is mass
The plasma density, the Langmuir probe measures independently.
Yes, but how do you know the mass? You can't get the mass from
The mass. Sorry, there we have a mass. There is a mass spectrometer on board. It's called CAPS. There's also another one called INMS, ion neutral mass spectrometer. The CAPS spectrometer is actually two instruments, one for measuring higher energy and one measuring as mass resolution. So we do compare also with that. From those measurements, yes, we compare. There's a whole series in this. It's an issue with several papers. But this is Langmuir data. And here the plasma escape was a little bit larger. For this heavy stuff here, it's something like 4 times 10 to 25. While the lighter ions was a little bit less, by a factor of 2. So if you have this as a dominant process, for instance, in the early Earth, then this would change by time the chemistry of the upper atmosphere toward more reducing atmosphere. We are, of course, looking at the details, what can cause these outflows, and in the heavy ion tail we see these broadband, extremely low frequency waves. We have not made a detailed correlation yet, so this is a bit preliminary. Here's another event where we see a little bit there, but specifically here, and this is Titan sits here, and it is just in the interaction region between the flowing plasma and the stationary plasma which we have. And we can actually tell what kind of phase velocity these waves have from interferometry between 2 antennas, which is electric field antennas, and it ends up around the ion acoustic speed, which we then believe is produced by an ion-ion two-stream stability, and that. So there is an interaction with the flowing plasma with the stationary dense ionospheric plasma, and you create waves which make the energy coupling between the two. And that then afterwards you have a flow out of the whole dense plasma. Okay, this was maybe a bit. Here we have a case where we can see cold plasma all the way out to maybe 7 Titan radii away. So that's something like 14,000 kilometers away. We have quite a lot of plasma which is escaping from Titan. It's an extremely fluffy object that disperses the atmosphere very rapidly. So one wonders where all these volatiles come from. They must come somehow from the surface, because for example, methane, with these kind of outflows, that they should disappear within 10 to 20 million years. But you have plenty of methane in the whole atmosphere, so you must have a source from the surface somehow. And okay, I go to the last subject, which is a new one, half-year-old, nothing published, well, some maybe, on the way out. And it has to do with the production of heavy organics in the ionosphere of Titan. And here on Titan, it's this first step from very simple molecules to somewhat more advanced complex molecules we are talking about. We are not talking about life on Titan at all. It's too cold, we think, and we have not seen an enhancement of carbon-12, for instance. It's probably a dead place. But we can learn something perhaps from studying the ionosphere and upper atmosphere of Titan from early Earth. Because there is plenty of EUV radiation and energetic particles that triggers this enormous kind of factory of organic molecules producing in the upper atmosphere. That's why we do this. This is from Forskning och Framsteg, actually. So the Cassini is going right through this region of ionosphere, where it's produced heavier and heavier. And the idea is that you have this radiation coming, and it breaks up this covalent nitrogen bond, which is very strong otherwise, and that further reacts with the methane, and that starts a whole chain reaction of organic chemistry in the upper atmosphere here. And then they are heavy, they diffuse downward, and they further react, and then they create the aerosol as well. But new measurements indicate you have an aerosol all the way up to the ionospheric altitudes, and you can see quite amazing data here. This is from the ion neutral mass spectrometer by Hunter Waite, PI, and this is from the first flyby, so it's about 1,000 kilometers. And okay, we saw H2Cm plus as a dominant ion, and C2H5 plus. But there are some indications that things are getting heavier and heavier the further down we get. Here, for instance, it's indication of maybe the benzene ion or some heavy nitrate here, and it's increasing the deeper you come in the ionosphere. Okay, so this is what the model, which are now severely outdated, has to be much more complex. You have some N2, there is some ionization, and you start to create mainly CH3 plus and C2H5 plus, and in the end you have some H2Cm plus as becoming the dominant ion. And this was existing before we reached Titan with Cassini. Now there are people like Véronique Breton, who have infinitely more complex chemical models here, and try to fit, and it can represent the simple organic molecules, which here, but we have severe problems of seeing the things I will come to and tell you about. Here we have from the mass spectrometer, this is altitude 900 to 2000 kilometers, and you have mass 28, that's H2Cm plus. We can see some peak around 1100 kilometers, but if you go up to mass 79, then you see and the peak has gone down further here, and you really expect something down here closer to 950 kilometers. And it was a little bit strange that they saw this dip here at the lower altitudes, because when we probe curve was rather flat in the densities here. So of course we went to do more detailed analysis. Also we saw the ion mass, average ion mass is increasing, and this one we can get from the MV probe. We get an average ion mass, but not any details. And it increases toward the bottom. and it's increasing toward 100, beyond 100. And 100 AMU was kind of the limit for the ion neutral mass spectrometer. So we compare the densities. There's number density. The blue is the INMS density, measuring ions up to 100 AMU. There is some, and the green one is the limit probe density, and then we have some checkpoints from other methods, by upper hybrid, etc. And the red dots is actually the ion density from the limit probe assuming spacecraft speed. They all end up here, but you have this dip here, and maybe there is a calibration offset of the INMS. But you surely have this dip here at the closest approach when you are as deepest down in the ionosphere. You can also see there is a mismatch in these deeper regions of the average ion mass. We see a little bit lower, larger one than the other side.
So the peak is about that's height approximately altitude.
This is below. This one here is below 1,000 kilometers. Or around.
Yes, and then the dip?
The dip is near 975.
Yeah. And the maximum corresponds to the ionosphere then?
Yeah, that's the ionosphere is actually starting between the here and here you have what we call the exo-ionosphere, which is escaping from Titan. And so the difference here is 1,500 to 2,000 cc. And that must be ions which are heavier than 100 AMU. And then the CAPS instruments see positive ions up to almost 40,000 AMU, 50,000 AMU. And the electron spectrometer is interesting. They actually start to see negative ions here with about the same mass. And it's dominating. Complete.
Negative ions, like H minus.
It's a heavy organic negative ions. At the same time, you have quite a lot of positive organic ions.
But aren't we talking about clusters rather than molecules?
Yes, clusters with both negative and positive ions. Yeah, ions border is when do you stop saying it's an ion? I mean, it's more like where we have in the mesosphere with water cluster ions, but in this case it's heavy organics, nitriles and hydrocarbon chains, which are charged. And the production is rather large. I haven't said so much about that, maybe I should. But anyway, this is the electron spectrometer, and it sees, in this region, it sees, unfortunately I didn't have their data here, so I couldn't show that, but it's published soon in Science. It was accepted in November. So, so you see these kind of signatures, which Andrew Coates, which are responsible for the electron spectrometer, believes is a signature of heavy negative ions. And that is up to these mass numbers. Sometimes, in this case, it's up to a few hundred AMU only, because this is the red one is an indicator of the very heavy ion, negative ions, up to 40,000 AMU, which we have, for instance, on this one, where you can see the red here. So it's it depends where you are in latitude, where there is much to investigate still here. This is first results, okay, brand new. So we have to figure out during what conditions, EUV, solar conditions, magnetospheric precipitating electron conditions, latitude conditions, etc. This occurs and what relationship it has with each other. It seems to be in the polar regions for a while. Yeah.
Why do you think it's surprising? If you find
Surprising? Yeah, it's more like the theorists didn't expect it. No, but we thought there was thinking by some that the photochemical reactions of neutral species would account for much of the aerosol, which you see below and view that. So we had a hope, but I think it's so much energy coming from the sun and from the magnetosphere into the ionosphere. So this is a kind of a catalytic production machine for organics. I don't know how you say that in chemistry, but I'm a physicist, a space physicist. Okay, anyway, conclusions. Lower ionosphere, below 1050 kilometers, at times dominated by well above 100 AU positive ions. At times there exist also substantial amounts of negative ions detected by the electron spectrometer. It's rather clear, we think, that the deep ionosphere of Titan is the main producer of heavy organic compounds for the aerosol haze, as well as deposits on the surface after the wave fuses down all these heavies. Key is the energetic UV radiation from the sun, as well as particle precipitation from the magnetosphere. It seems to be a factor of about 2 to 1 for the production of the ionosphere. And together with the nitrogen and methane atmosphere, and we think we can learn on early Earth chemistry from the Titan studies. I'm not sure how much further we can do on Cassini. It has to do with limitations on the INMS, ion neutral mass spectrometer, which only reaches up to 100 MU. But CAPS is working on it to try to have better mass spectrum. And really, if we just add water, this can lead to hydrolysis and prebiotic building blocks, amino acids. But on Titan there is almost none. Maybe there is one amino acid which doesn't contain oxygen, but maybe can be expected there. Otherwise not. And H2CN plus is otherwise the dominant ionospheric species, where from most of the chemistry comes from. Okay, I think that's enough. Thank you.
So, question please.
Is there no oxygen at all? I mean, like in CO2 or something?
Yeah, there are CO2 and H2O, water, and carbon monoxide also, but it's parts per billion.
Okay, so there's no oxygen virtually.
Well, virtually not. Well, there is, but not. It can be explained by meteoritic infall, basically. Radiation.
Yes?
Yes.
The erosion of the Northern atmosphere. But we heard recently from, I think, on Mars Express, that the escape is far less than calculated by orders of magnitude.
Yeah, that's Stas Parbash and Richard Lundin's latest results, yes.
So the numbers you showed there in the beginning was before that experiment, I think.
Those numbers are still valid, I think. Yeah, okay, I can't. It's something like 0.5 kilo per second, right? And those values come from a person that should know, and that's Yama, who sits beside Stas. So I think it should be right. But on the other hand, you're right, there is such a paper and claimed by Stas Parbash and Richard Lundin. I cannot account for them to the knowledge.
What is actually the density scale height of Titan? I would have thought it's actually rather small. I mean, I'm surprised that the ionosphere has such a large radius. I would expect the scale height is really much, much smaller.
Yeah, it's true. It's a very fluffy object. I mean, on Earth it's a kind of a extremely thin layer, the atmosphere, but on Titan it's of the order of if you go up to the exobase, it's around 1,400 kilometers. That's half a Titan radius. So it's
That's very strange.
it's a very, very fluffy object.
Yes.
So it's not in hydrostatic equilibrium, you mean?
No.
But what are the forces that sort of keeps it in position then? I mean, the scale height is-
No. You have sorry. You have an exobase. Oh. This is exobase. 1,400. So collisions dominate below. So there you have an equilibrium, right? And above collisions don't dominate. Now the ionosphere is kind of
So it's really popped up by
yeah, and the gravity is rather low. I mean, it's okay. It's very cold, and it's a low gravity, which makes it so fluffy.
Is the radius
But the upper parts of the atmosphere is not in equilibrium. So you have an enormous exosphere out to 10, 20 Titan radii, which are as a kind of a corona around Titan. No.
Yes.
So Titan sits next to a fairly big planet.
Yes.
So the circumstances should be a bit different from where we are. What is the influence of Saturn?
Now the distance is 20 Saturn radii, so it's rather far out in the outer magnetosphere. So what Titan sees is the co-rotating magnetosphere. It comes with about 120 kilometers per second. It varies rather much in dynamic. So it's similar to a flow hitting Mars or Earth. In this case, we have a subsonic flow, so there's no bow shock coming up. While on Mars and maybe on the Earth, there's not going to be any bow shock because it was a supersonic flow from the sun. But that's the only main difference. There's also a magnetic field associated with this flow, which one can make parallels with the anti-magnetic field. Yeah.
What's the composition of the solid part? I mean, the real Flemish solid. Does one know?
The composition of the solid. Now I have to dig down. It's mainly an icy body. It's believed to have some kind of stony core, and then maybe have some layer of kind of ocean, water, ammoniac ocean underneath the icy surface. One have seen water volcanism, and there is a lot of tectonic scars on the surface. So there seems to be an internal heat source, probably due to the gravitational interaction with Saturn. It heats the interior, and then you have gases and water lava flow at 0 degrees and such on the surface. And you can clearly, there have been released pictures which show this rather nicely. I can show you maybe. Is that sure? Yeah. I have a few maybe. Let's see. Yes. No. Something like. Let's try this one. Slow.
Mats' question related to that?
Yeah,
No.
but Lundin and they were presenting these results at the Academy about a year ago.
Who?
Lundin and Barabash.
Yeah. But Yama's claim is from just a couple of months ago.
The article, yes.
So, how do you get through that? There you go. See if I can see some writing pictures. Okay. Yeah. Oh yeah. Okay. Good enough. So here is some pictures of methane lakes in the polar regions. This is from Earth. This is from Titan. I guess this is Lake Ontario. So it's the same kind of size. So you have lakes and such. And this is a claim of a water volcano. The region here is warmer, and one thing is it's a geyser. It comes up water from cracks in the ice. And this is just Hurgeon's Landing. Here's one of the first pictures. You can see rivers, or not too long ago rivers of methane which have been flowing on the surface. Here first one thought it was an ocean. There's totally false. It seems to be a kind of a wet ice, kind of a marsh, rather damp. Here you see kind of a fraction crack, and then you see kind of a flow here, and this is water ice, they believe, that has been flowing in not so far recent time. So it's an active geological body, as I've understood it. This is the Stockholm skärgård. This is kind of a mosaic of the lander, and you can see, one could see methane haze. Here was the landing site, just beside one of these flat plateaus with the kind of methane wet ice, and these are most probably ice mountains, water ammoniac ice mountains. So once in a while there has been some kind of flow here, they believe, because on the landing site, this is 10-15 centimeters, they could see lots of these stones, or it's actually ice clumps that has been brought there by something that has been flowing in the past. And some claim that actually part of this was liquid.
I was wondering, when you would probe, you mentioned you can measure the electron density, but it seems like you also measure the electron temperature. Oh, sure, it must be more difficult.
Somewhat. It's about 20% error in the electron temperature we have. And we also can achieve the ion ram flow, and from that we can also estimate the ion mass, certain conditions there. So we have the density, the temperature of electrons, and also the ion flow.
But to measure the temperature, you must somehow measure the distribution of speeds.
Oh yeah, in the we measure the temperature you can get in the dense plasma, meaning more than 100 cc particles per cc, and what you do is you integrate the distribution function. I mean, you have a probe with a potential, and you have kind of a region around the probe where you sample the electrons to the probe. So you have to integrate the presumed distribution, which is usually kind of a drifting Maxwellian, to get what kind of current you would expect. We have So we are sensitive to the distribution, and we can differ, we think, between kind of bi-Maxwellian distribution. We have seen cases where we see two temperatures but the same density. It looks like this. Okay, so it's kind of a two-step. This is U bias, and this is the sampled current. And this part for positive bias, that's where we sample the electrons. This is the ions and the photoelectrons from the emitted by UV light. So we can actually get the UV intensity this way. But so sometimes it looks like this, and if you take the derivative of this, then you have something that goes up like this and continues like that. Then you have two potentials here, characteristic potentials. You can get two electron populations doing that. And from that we get two temperatures and two densities. So we have some ways of deriving the electron temperature also for non-Maxwellian. Oh, it can vary, but in around 1,000 kilometers is around between 500 and 1,000 Kelvin. So higher up it's of course warmer, and but the methods start to fail when we start to approach few eV. So in the dense magnetosphere we cannot derive an electron temperature, but the ionosphere we perfectly get. That's very important for chemical reaction rates, I guess.
So the fact that it's warmer higher up, is that because the photoelectrons, they don't thermalize?
We have a lot of photoelectrons, especially in the outer magnetosphere, it's dominating. But we actually use it, so the normal derivation of parameters in those cases we cannot do. But what we use then is actually the floating potential, which is around here. And we get the values if we're sweeping of the probe to spacecraft potential. And so we can monitor the spacecraft potential. And then we calibrate versus the electron spectrometer densities. And then we have a proxy for the electron density wherever. And that is a rather good one. It is in certain cases when you have energetic particles hitting the probe, you see distortions. But in most cases you can derive. We have a model now, which will soon be published of all the densities in the magnetosphere of Saturn, model for Saturn's electron density, so, which we have done this way. So it's very, very powerful. The electron temperature there we can't. This electron spectrometer much better. It's higher.
Okay, so that was very interesting, and so then let's thank Jan Erik again.